It's hard to recover from that. Okay, now if you want to know exactly what my expectation will be for this, I'm going to show you. I mean, I've given you what the questions are going to be like, right? I'm not trying to keep that from you. This is what I want you to be able to do. So let's start by remembering that if you want to find the acceleration of gravity on the surface of a planet or the surface of a moon or something like that, do I have everybody? Okay. The idea here is that to find the acceleration of gravity on another object, we're setting the net force equal to ma, where this a is the acceleration due to gravity. So it's like if you dropped something on a moon or on a planet, it would fall because there'd be an unbalanced force on it, and that unbalanced force would be gravity. So that's why we're saying net force equals ma. I joked about dropping one of you onto the planet. So it's going to accelerate downwards. Now, the force we're talking about here is the force of gravity. So in the case of this one, which is Europa, it'd be the mass of Europa, the mass of you, g, and the separation distance squared between you and Europa. That has to equal m, and I'm going to change that a to a g to reflect that this is the acceleration of gravity. But I'm also going to put a little e here to remind me that we're talking about the acceleration of gravity near the surface of Europa. Which m do we put here? What's that? The mass of u, the thing that's being dropped. So this is the one that gets the little y. And that way we cancel out that mass because look, it's not a surprise. Everything near the surface of the Earth falls with the same acceleration. It would be like this on other planets too. The acceleration would be different, but all the objects would have their own would be the same acceleration near that surface. Now, that's really it for this one. So mass of Europa, g over the separation distance squared. And for the separation distance, we're talking about you being right near the surface. So it's the radius of the planet that we put there. So RE for Europa. Okay? Now, again, then you have to put the numbers in, and that's where you guys are sometimes a disaster. But this is the first step. Now, ready to go on to the next step? What do you need, Betty?
How did you decide that it was like the mass of you and not get canceled?
Well, I need to drop something. It's a thing being dropped near the planet. So I wouldn't put Europa. I'm not dropping Europa near Europa. I'm dropping some object near Europa. So it takes two objects to create gravity, but we're looking for the acceleration of one of the objects. And this is the object that we're dropping. That's why. That okay? So you're gonna write that down or something so that you know and you can study it. Okay. Now, the next thing I asked you is to figure out how fast the planet was going around how fast the moon was going around the planet. So you gotta zoom out a little bit for this one because we're talking about the circular orbit of Europa around Jupiter. So Jupiter is really, really big. And you have lots of options for moons around Jupiter, so I just picked one of them. One of the ones I think is more interesting. So, Jupiter. And we have our moon going around Jupiter. Now, this problem is different and has some different parameters. This is a net force equals ma problem again, but we're looking for its tangential velocity. We're looking for how fast the moon is going around the planet. So for this one, this A is not any A, it's AC because we're talking about centripetal acceleration. Now, still, the force causing this is the force of gravity. There is a gravitational force towards the center of curvature. And this is what's causing the centripetal acceleration. So this will be the mass of Jupiter, the mass of Europa, g, over the separation distance squared. And this has to equal m vt squared over r. And this is how we figure out how fast it's going. Now, as I said on Monday, there's a couple things here that you have to consider. For example, which m are we talking about now? It's Europa. This is the thing going around the circle. So whatever the thing is that's doing the orbiting, that's the mass you put here, because this is the mass that has centripetal acceleration. That would be Europa. The next one is a little bit more challenging for some of you because it's hard for you to picture this, but this is the separation distance between the centers of the two objects. This is the radius of curvature of the path. Now, they can be the same, but in order to be the same, the thing at the middle has to be much bigger than the thing that's orbiting. Now, for everyone we are doing currently, that's going to be true. Second semester, it won't be true. We'll deal with problems in which it's not true. But first semester, we're going to say that the mass in the middle is much greater than the mass orbiting. And if that is true, then separation distance equals radius of curvature. Okay? If it's not true, you'll be told it's not true. You won't have to fake it. You won't have to guess. You'll be told it's not true, that you will have to find the center of mass of the system. So that means, though, this becomes the same r. So I replaced the little r with the big R. And what is that separation distance? It's a separation distance between Europa and Jupiter. Now, that cancels out one of the r's, and it still cancels out the mass, so you get mass of Jupiter times g over r equals vt squared. Now, keep in mind, at the end of that, you have to take the square root of both sides to get your actual answer. But also, you got to use the right numbers and know that you're going to get an answer that's in meters per second. Don't forget your units. Now, the last step to this is not particularly hard either, but I asked you to find how long it takes for Europa to go around Jupiter. Well, that's just using some, this is not necessarily physics, this is just distance over time. We just found the velocity. We know the radius of curvature. You just have to solve this for t. The thing about this is, when you solve this for t, you get an answer that's in seconds. So if you want to get the correct answer, you'll have to probably put it in appropriate units, which means keep dividing by appropriate units so you get something that, is a small enough number to make sense. For this one, it's 3.5 days or 3.6 days. That seemed like the right place to stop because it was like 80-something hours. Something small today. And I don't want to spend a lot of time on it. And when I say small, I mean quite literally, we're talking about 5-6 minutes. I want to talk to you about center of mass. Center of mass is supposed to be introduced in this chapter, but it used to be that we introduced it in a different unit, in Unit 5. Unit 4. In addition to that, we used it a lot in Unit 5. They want to introduce now, and I know it's possibly going to be on the semester exam, so I want to make sure I've introduced it, and I'll reinforce it a little bit as we get close to the semester exam. But we're going to talk about the center of mass. The center of mass is also called the center of gravity, and it's a place. I want to emphasize before I get started, the center of mass is a location. It's where the average mass of the object is. I'll say that once more, but that's what center of mass means. It's where the average mass of the object is. What are you tearing? Okay. But it's a location. You're looking for a place. So even though the center of mass sounds like you're finding a mass, you're not. You're finding a place. Now, finding the center of mass is actually a three-dimensional process. So if you have an object in space, there's the center of mass in the x direction, y direction, and z direction. The most you'll be expected to do is the center of mass in 2 dimensions. But our example today is just going to be one-dimensional. And this is what a center of mass problem will look like. Or here's an example of one. Imagine I have 3 boxes, and they're all on like a very thin, light plank. And one of them is 3 kilograms, one is 8 kilograms, and one is, let's go with 4 kilograms. Okay? So I have 3 objects, and they're all on this really light plank. And I want to find the point where this plank would balance, like a teeter-totter. This is a center of mass question. We want to find where the center of mass is. Okay? Now, before I even launch into this, I want to remind you, center of mass is a place. Because it's a place or a location, you have to decide how you're going to measure that. Meaning, if I say that center of mass is 1 meter, what do you mean? When you give the center of mass, you say the location, but you say from somewhere. For example, I could pick and say this is where 0 is, and say I want the center of mass from the 3 kilogram box. Or I could say I want the center of mass compared with the center of the plank. I have to give some reference point. So let me give you some distances. Let's say these 2 are 3 meters apart, and these 2 are 5 meters apart. And now what I'm going to give you is the equation for the center of mass, but don't get scared away, okay? Some of you will get scared. I'm going to do it just in 1 dimension. I'm going to say give you a 1-dimensional version of this. Notice I use x to represent 1 dimension. I put a bar on it because it's a vector, and I put cm saying it's the center of mass of just the x direction. The top looks like this. You take the mass of each object and multiply by the location of each object in the x direction. And you start with object 1 and you end with the last object. Then you divide by taking the mass of each object, starting with object 1 and ending with the last object. I don't know if you guys know summation notation or not, but you're supposed to. So I'm going to use that because this is how it's recorded on your equation sheet, and I want you to recognize it. But there's not much here. A summation is exactly what it sounds like. You add things together. So the top one says take a mass and a displacement and multiply them, and then take the next object's mass and displacement and multiply them, and then take the next object's mass and displacement and multiply them, and then add all those things together. It says to start with the first object and end with the last object. That's what the notation means. The bottom of this one's even easier. It just says to add up all the masses. So take mass of object 1, add it to object 2, add it to object 3, and keep going until you get to the last mass. That's all this means. However, before you can do a problem like this, you have to pick where 0 is. X is a number line. So you have to pick a point that you're using as your reference. And it can be anywhere. Now, normally in a problem, they'll tell you where's the center of mass relative to the blue box, or where's the center of mass compared with the yellow box. So they'll give you a point of reference. But whatever you choose as your point of reference, you're making the point of reference 0. So I want to tell you something that you're not writing down, but you should. This is a vector. So when I choose where 0 is, let's say I choose 0 to be here, I also need to choose what direction is positive and what direction is negative from 0. Because this is a vector value. So I have to give my vectors in directions. So that's especially important if I say made this one 0. Then any mass over here would be negative, and any mass over there would be positive. It's not the mass that's positive, it's a displacement that's positive. So let's do this one. This one's not particularly hard to do, and I want you to see how it goes. And we're going to do this relative to the blue box. We're going to set the blue box as 0. And we're going to say this direction is positive. All right, so we're going to use this formula. We'll do the top part first, then we'll do the bottom part. How many things are we adding together on the top? How many boxes are there? So we're adding 3 things together on the top. How many things are we adding together on the bottom? How many boxes are there? Okay, not tough. All right, first object is a 3 kilogram mass. Where is it located? It's at 0. So we take the mass of the first box and where it's located and multiply them together. And you get an advantage if you choose one of the boxes as being 0, right? Because you multiply by 0. That's always good. We're going to move on to the next box. What's the mass of the next box? 8. How far away is it from the reference point? 3. So I'll multiply by 3. Moving on to the next box. What's the mass of the next box? How far away is it from the reference point? 8 meters, right? We're not going to put 5 down. We're going to put 8. Okay, good. I fooled 6 period. Many people said 5. Good for you guys. All right, let's do the bottom. What's the mass of the first box? What's the mass of the next box? What's the mass of the last box? Excellent. This isn't tough, right? So, not yet. Well, I mean, it can be tough. Like if you find Earth and Moon, you're going to use those big numbers, right? The center of mass between the Earth and Moon is going to be a hard one because you've got the big numbers. This one, not so much. 3 times 8 is 24, and 4 times 8 is 32. It's 56, right? If you add it all together, 56. And that's kilograms times meters. Divided by 3 plus 8 is 11 plus 4 is 15. So 15 kilograms. So now I divide 56 by 15. I get 3.7 meters. Perfect. So it's 3.7 meters from the blue box is where the center of mass is. So, somewhere like right there. Go ahead. The kilograms cancel out. Remember, at the end of the day, this is a location. Okay? So that's the simple way, that's a simple thing. You have a couple of questions on center of mass. I want you to do them. But I also want to talk about this, what they might do. And this is something that's not uncommon. Not really, but so imagine you take a paper clip and you bend it into a square. Okay? Where's the center of mass? It's in the center, right? This has symmetry. And because it has symmetry, we can kind of figure out where the center of this thing is, right? Now, a very common question is to take something like this and say, what if you bent it like so? Okay, so I bent it, and it'll say, where is the new center of mass? A, B, C, or D? So you're correct in saying before that the center of mass was in the center, but now we've bent it. Can you figure out where it went? A, B, C, or D? No, it's totally a rational thing to think about. Did this piece of mass got shifted upwards and to the left, right? Because the middle of this object was here, and now the middle of this portion of the object is there. So its mass got shifted upwards and to the left. Which of those makes the most sense of where the new center of mass is? A. Yeah, I know it'd be A. Do you see why, though? Okay. That is the most likely kind of problem you're going to see on an exam for center of mass. most likely. But again, the whole idea is that each one of these pieces has kind of a center. If you break it up into equal pieces, all of these have their own center. I broke it up into those size pieces because that was the size that was bent. And when I moved it, I moved the center upwards and to the left. All right. Let me tell you how you should approach this question, okay? So it's referring to a modified outward machine where you have a block on a table and there's no friction and a block that's hanging off on the side. And so in that question, our table, the block hanging off the table, the block on the table, and a ideal pulley and a light string connecting them together. Okay. So we're assuming, or they tell us, that there's no friction in the problem. And this is the mass on the table, and this is the mass that is hanging. Right? I want you to understand what they're getting at here, okay? And this might be tough for some of you because it involves the idea of limits, the limit of something as one of your numbers changes. So to solve this, I'm going to ignore the up and down forces on the mass on the table because there's no friction. And I'm going to draw tension to the tension to the right. And that's the only force that's acting horizontally on that mass, but it's accelerating. So tension equals mass on the table times A. Now the one that's hanging is experiencing weight downwards, mhg, and tension up. That's right. It too is accelerating, and I'm going to make this the positive direction, so mhg minus t equals what? Yep. And I'll put h there and remind me that that's the hanging mass. They're asking me about what happens to the acceleration, or if the acceleration can ever be zero, stuff like that. They're asking questions like that. So let's get an expression for the acceleration. I'm going to do so by adding these two things together and solving for A. The t's cancel out, and I wanted that to happen because it's an unknown, because they're asking me about the masses. So mhg equals, we'll do it this way, do it the long way, mh plus mt times A. So A equals mhg over mh plus mt. Now, notice G is like in this, right? I'm going to just move G over here. So it's kind of by itself and focus on what's in here. Because that's what we had before. I know some of you don't think that that's mathematically the same, but it is. Okay, but this helps me focus on this part, right? G is G. It's not going to change. It's going to be 10 meters per second squared here on the Earth. The question is there ever a time when this equals zero? Because they asked, is there ever possible that you could have a situation in which the acceleration of the system would be zero? It would never be zero, but what if the mass on the table was like a cement brick and the mass hanging off was a paperclip? Would the paperclip be able to move the system very much? Now, even without friction, it would be really hard because I'd have something really, really big in the denominator of my fraction and really, really small on the top, right? That's because what I'm saying is, what if the mass on the table was much bigger than the mass that's hung? Would it be zero? No. Would it approach zero? Yes. If I wanted to make it as small as I could, as close to zero as possible, I'd have to put a really, really, really heavy thing on the table and then hang something super light off the table. Would it be zero? No. Would it be close? Yes. Right? That's what we mean by a limit. A limit as one number gets way big compared to another number. And that's because it's a fraction there. You see what I'm saying? They also ask, is it possible that the system could accelerate at g? Well, for it to accelerate at g, everything in the brackets has to be equal to 1. Is there ever a chance everything in the brackets would ever be equal to 1? No. But what if the mass that's hung is much bigger than the mass on the table? What if I hang the cement brick and put a paper clip on the table? It's going to be close, right? Because I'm going to have mass hung really, really big, and then mass hung plus something really small. That'd be like, what if I had 1,000 divided by 1,001? That's still pretty close to 1, isn't it? It's not perfectly 1. Is it exactly g? No. Is it close? Yeah. That's the idea of limits. So the problem is trying to play with that. And yes, they asked this on the AP1 exam about 5 years ago, this exact question. And they asked specifically, could the acceleration ever be g? And you were supposed to say, well, if the thing you hung was much, much greater than the thing on the table, it would get close to g. And then they asked, could the acceleration ever be close to 0? Well, if the thing on the table was much, much greater than the thing that you hung, it'd get close to 0. And then, part C, they had you solve for it. Like they had you do the math with an M1 and an M2. And then they said, does your equation agree with what you just said in part A and B? And you'd have to say, well, yes, it does. Why? Because the denominator gets really, really big when MT is much bigger than MH. And it gets really, really close to 1 when MH is close to MH is much bigger than MT. They're expecting you to do that. Go ahead. Is this question? But there's friction here. And because there's friction here, I am going to have to care about the weight and the normal force because it's going to change what we do. So our answer is going to be different because of that. Not much different, mind you. Most everything that we have here we're going to reuse, except now the net force in the x direction equals ma, and the net force in the y direction equals 0. Now, we only have a minute or so left, so let me just state this before we go any further. What I'm about to do now assumed that I tapped the block in this direction and gave it a starting velocity that was to the right. That's why my friction is to the left. If I had tapped the block in the other direction, right, then my friction would be to the right. So I purposely think that the best way to do this problem is consider tapping it this way. They will not leave that up to you on the test. They will say, given an initial velocity to the right or left, they will tell you.